Hello and welcome to lecture number 30 of the course Theory of Computation. In the past couple of lectures, we saw Turing machines and we saw the standard model of Turing machines with single tape. Then we saw multi-tape Turing machines. In this lecture, we are going to see a different type of variant, which is non-deterministic Turing machines. So the Turing machines that we saw was deterministic. But now we are going to see non-deterministic Turing machines. So this it is similar to the non-determinism that we saw in two previous machine models, right? So we saw deterministic finite automata, and then we saw non-deterministic finite automata. Then we saw PDAs, push-down automata, which also had non-determinism built into it. Similarly, we have non-deterministic Turing machines, right? So the main difference between deterministic and non-deterministic Turing machines. So we'll assume just one tape, single tape. So the point is this, that if you are at a certain state, let's say you are reading a symbol A, right, and you are at a certain let's say state Q8, right. In a deterministic Turing machine, delta Q8 of A is defined to be something, let's say Q9, let's say D, and you move left, right? But in a non-deterministic Turing machine, there could be multiple things that you could do. So perhaps Q9, D left could be just one of the options. The other option could be Q5, I don't know, C left, maybe something else, Q4, C right, right? So there could be multiple choices available, right? Not just one option. The number of choices available could also be 0, right? Just like if you recall in NFAs, for the current state and the symbol red, you could have multiple choices, you could have just one choice, or you could have 0 choices also. Similarly, same thing here, you could have multiple, just one choice or 0. Formally speaking, in the case of in the case of deterministic Turing machines, we have the same 7 tuple: Q, sigma, gamma, delta, Q0, Q accept, and Q reject. Same thing here. The only difference is in the way delta is defined, right? So in the case of deterministic Turing machine, right, deterministic Turing machine, we had delta we had delta from a function of Q cross gamma to Q cross gamma to left right. Here, instead of Q cross gamma cross left right, we map to the power set of Q cross gamma cross left right in the case of non-deterministic Turing machines. This is because there could be multiple options, right? So either you could go to Q9 right D then left, or you could do, so if you just consider this as the two choices, right, this Q9 D left or Q5 C left. So you could do that or this, right? There are two options listed here, but there could be more than 2 also. There could be 0 also, there could be 1 also, right? So as a result, what happens is that the starting configuration is fixed, right? It is the starting state followed by the input symbol, right? So the starting configuration is input string. So you have W1, W2 up to Wn, and you are the starting state, let's say Q0, sorry, this is too small, Q starting state, Q0, and then the head pointing to the first location. So this is the starting configuration, which I am calling it C0. And in case of a deterministic Turing machine, these conditions were the same. When does a string get accepted? A string gets accepted if there is a sequence of configurations such that C0 is the starting configuration. Each move is valid. Ci to Ci plus 1 is valid. Ci plus 1, C0 to C1, C1 to C2, C2 to C3, and so on. And finally, Ck is an accepting configuration. By that what I mean is Ck contains the accept state. Same thing here also. There should be a sequence of configurations just such that C0 is a starting configuration. All the C1 should be a valid successor of C0, C2 should be a valid successor of C1, and so on. Finally, the CK should be a valid accepting configuration, meaning the state should be the accepting state. So, what is the difference then between deterministic and non-deterministic Turing machine? The key difference is this: in a deterministic Turing machine, we had something like this. We had the starting configuration. The starting configuration completely tells us which move to take, meaning you know the state, you know where the head is pointing, you know the next state, you know the next what to write and where to move. So the starting configuration tells us what is the successor. That successor tells us what is the next successor, and so on, right? So the computation goes in a kind of a linear path, and finally you reach some state which could be accepting, or you never reach anything, right? However, in a non-deterministic Turing machine, let's say C0 could have multiple states as successors. It could have, let's say, let me just write D1, D2, D3, many states as successor. Each of the D1, D2, D3, D4 could also have further many states. So now, when do we accept, or when do we accept? We accept when we can find a computation path, something like this. Sorry, this is too thick. We accept when we find some computation. Okay, this is too thin. we can find a computation path, something like this, finally leading to an accept state. So this should be an accepting state. So, or accepting configuration, right? So some computation path has to be there. So there are multiple configurations that are valid successors of the starting configuration. For each of these successors, there could be multiple valid successors themselves, and and so at the end there could be multiple possibilities. Some of them could be reject, some of them could be accept, some of them could be reject, and so on. All that you care about is there at least one start to one path that leads to an accepting configuration. So you accept, we accept if there is one, by one what I mean is at least one, if there is at least one computation path that leads to an accepting configuration. So there could be multiple such accepting configurations, but as long as we find one, we are good. Like it could be that like all the configurations are rejecting configurations except one. That's also good enough. So we say that non-deterministic Turing machine accepts even if there is one computation path that accepts, right? So here we had just one computation path that accepts. Even then we are fine, right? Okay, here there are other computation paths, that's okay, but we accept if there is at least one computation path that accepts. We reject if all the paths are rejecting. Okay, if none of the paths accept, we say it is rejecting. Okay, so that's the thing. So there is a certain asymmetry happening here in the between the accept and the reject. We accept if at least one path accepts, and we reject if all the paths, none of the paths are accepting, right? So there is this, so it is not like one path rejects, you reject. For rejecting, you want everything to reject. For accepting, you just need one accepting computation path. So non-determinism should be thought of, like I have said before, as somehow a magically, like if there is a non-deterministic Turing machine, it somehow magically finds the accepting path, right? A non-deterministic Turing machine, you should not think of it as trying out all these paths. No, that's not how it happens. It somehow magically is able to do all these paths in parallel, right? So if you see here, there are like multiple paths, one in the left, one in the right, one through middle, and so on. It will try out all these possibilities and magically find the correct path, correct accepting path if it is there. So the time taken by the non-deterministic Turing machine is also the length of this accepting path, not the sum of the lengths of all this. Okay. So maybe some examples will make this clearer. Let's see one example. So in this example, we are testing for compositeness, meaning you are given an integer, a number. We want to see whether it is composite. So the given number is W, and we want to see whether W is a composite number. Composite meaning it's not prime. So for instance, 20 is a composite number because it can be written as the product of two, like 10 into 2 or 5 into 4, right? Because so if it's a prime number, let's say 29, the only possible way you can multiply it, write it as a product is 29 times 1, right? Composite means not prime. So the idea that we do here is this. So you're given W, you're just going to guess two numbers x and y and check whether x and y is the product of x and y is W. Okay, so if the product is W, then we know like if x and y and neither of them is 1, then we know that W is a composite number because we are finding a non-trivial factorization of W, right? So what we do is this. So how do we actually guess x and y? So suppose W, so the way W is given, it has n bits, right? So W1 to Wn, n bits. So first we are going to write x on tape. So since the length of W is n, we are going to write an n bit number for x. So it could be anything. So you decide whether, so you decide like this. You first write 0 or 1, let's say you write 0, then you write 1, then you write 1, then you write 0, then something like that, you write some n bits. Okay, so there are two possibilities. Each bit you could write 0 or you could write 1. So it's like this. So you are traversing through this computation path, right? So it's like you first you go left or right, two possibilities, and for each of these two possibilities there are two further possibilities, right? So if you go left, then you could go left or right. If you go left right, then you could again go left right, and so on, right? So there are multiple options. So assuming this is n bits, right? This tree represents 2 power n possibilities, right? So you take the tape. So this is what you are doing. You take the tape. You take the tape and you first write x, which is n bits. Then check whether the number that you wrote is strictly greater than 1. Or you check whether it is 1 or 0. If it is 1 or 0, then you are not going to get a non-trivial factorization. So then you reject. So it's okay if you reject because all you need is one accepting computation, right? And then you write a y. Again you write some numbers that says 1, 0, 1, 1, 1, something, right? And again you check whether that number is strictly greater than 1. If it is strictly greater than 1, you continue. If it is not strictly greater than 1, meaning if it is 1 or less, you reject, right? So that's what I am saying here. If x is 1 or less, you reject. If y is 1 or less, you reject. So you guess x, you guess y. So by guessing the word guess, I mean non-deterministic choice. So you could either write 0, 1, then again write 0, 1, and then again write 0, 1, like that n times, and then repeat it n times again for y. So there are n choices made for x, n choices made for y. So basically you are guessing all the possible 2 power n paths of x, right, and all the possible 2 power paths for y. So what I meant earlier is that this path, the all 0 path that comes on the right side, this will be a reject because this gives us 0. This is not going to result in a valid computation. Even the one that goes 0, 0, 0, 0, 0, finally 1, that's also reject because that's also, we want something more than 1, right? But this is just x. Now for each of this choices of x, right, now there will be another tree. So let me just take one possibility and another tree. So this is the choice of y, and there will be 2 power n possible choices. Let me just rewrite it. Choices for y. And finally, so I'm just writing the 2 power n choices like this. Right. So now finally, for each of these choice, you can check whether x multiplied by y is equal to the w. So then if it is equal, you accept. If it is not equal, you reject. So like that. So just to give a concrete example, let's say you take the number 27. Okay. So 27, we need 27 is less than 32, so you need 6 bits to represent 27, right? So 6 bits. So then you guess what 2 6-bit numbers. Let's say 101 101 something, right? And then 00101 or something. So this number, if you check, what is it? Let's see, 16 4 2 16 8 4 2 1. I'm sorry, we don't need 6 bits, you only need 5 bits. So let me just write this. So now 16 8 4 2 1 8 16 8 4 2 1. So 16 plus 7, this is 23, and this is 101, this is 5. And so 23 multiplied by 5 is not 27. 23 multiplied by 5 is 115. So this path will lead to 23 multiplied by 5 is 115, which is not 27. So this will be rejected. Whereas if you guess, let's say 01001 and let's say 00011, see, this is 9 and this is 3, and this will be accept. So we will guess many guesses, we'll make many guesses which are wrong, but since 27 is a composite number, there will at least be one set of guesses, at least be one. There could be more, right? So 27 can be written as 3 times 9 or 9 times 3, 2 different ways. So there will be at least one set of guesses which will lead to, which will certify that it is a composite number. And even if there is one set of guesses, you will say that it is accepted, right? So, but however, if you take, let's say 31, right? 31, there are no ways to factorize 31 other than the non-trivial factorization. You can only write it as 1 times 31. So whatever path you take, whatever numbers you guess, you are not going to get 31. The only possibility you get is 1 times 31, which will anyway be rejected. So this all paths will reject for 31. Whereas for 27, there will be at least one accepting path. So that's how you use non-determinism to decide whether a number is composite or not. Once again, it's not like the machine is serially trying to do all these different computation paths. You have to think of the machine just magically trying out everything and figuring the correct path if it exists. All it needs is one path that leads to an accepting computation, accepting state, right? Once again, it guesses x, it guesses y. If either one is 1 or less, it rejects. And then it tries to multiply. If the product is equal to w, you accept, otherwise you reject. So if w is indeed composite, there will be one guess for x, at least one guess for x and y, for which we will get the w to be the product, and then you will accept. Right. So that's how you would accept, or you would test whether a number is composite. Okay. This can be done for using deterministic computation also, but since the objective is not deterministic computation, we are presenting it in a non-deterministic fashion. Okay. So the next thing is a clique. So what's a clique? So we have a graph, right? We have a graph, and so this is a graph. You have these the one that I've drawn here. You have vertices, which are these dots, right? And you have edges, which are joining these two dots. So this is an edge. This is an edge, right? This is an edge. So an edge connects two vertices, right? And we say a set of vertices is a clique, right? If all the vertices are adjacent, meaning all the vertices there is an edge connecting them. So S is a set of vertices. S is a clique if for all u comma v in S, uv is an edge. So for instance, I'll just draw one example. Maybe we'll just draw one example. So these three vertices form a clique, because if you see these like any two vertices, there are three vertices and they form a triangle of sorts, meaning any two that you take, they are connected by an edge, right? Another example is these four vertices. This also forms a clique, because any two that you take, there is an edge between them. So the goal is, you are given a graph. Let's say this is the graph G, right? And you are which has n vertices and a number k. The question is, does this graph have a k clique? So in this, if this is the graph, this has a 4 clique which is marked, but it does not have a 5 clique. At least I think it does not have it, but you can check it. I think it does not have a 5 clique, right? So if you are given a graph, if given this graph and the number 4, you can answer that it does not have or it does have a 4 clique. But if you are given the number 5 or number 6 or any higher number, you can say there is no 5 clique or 6 clique, right? So that is the goal here, right? So this graph has a 4 clique, meaning a clique of size 4, but no 5 clique. If it does not have a 5 clique, there is no scope of having a 6 clique, right? Or a bigger clique. Okay, so this graph does not have a 5 clique, but so 4 is the largest size clique. So of course you can test for it deterministically, meaning you can, if there are n vertices, you can check, and let's say k is 4, you can check all possible subsets of size 4, right, which is like roughly n choose 4 subsets, and then test in that 4 set of 4 vertices, you can check whether all the edges are present, right? So but this will take n choose 4 time, which is kind of high, right? Order n choose 4 time, which is kind of high. So now non-deterministically you can do it faster, right? Also it will help to illustrate the non-deterministic, the notion of non-determinism. So before that, I just want to explain how a graph is represented, right? So graph has to be, you cannot give a graph as a picture to a computer, right? So if you have taken a data structures course, you might have seen these terminologies. One of the standard ways to represent a graph as a computer or to a computer in a computer program is by an adjacency matrix. So if a graph has n vertices, you give an n by n matrix. The matrix has only 0, 1 entries, right? So for example, so there is a graph here which has 4 vertices, right? So and the adjacency matrix A is written here, right? And since the graph has 4 vertices, the adjacency matrix is of size 4 by 4, right? And basically you put let's say this entry, maybe I'll just highlight something. So this entry is 1 because it's second row and third column. This is 1 because of this edge, right? This because of the edge connecting vertex 2 and vertex 3, right? And the same entry, the 3 2 is also 1, the entry 3 2, because the third vertex connecting to the second vertex, because this is an undirected graph, which means an edge from 2 to 3 is the same as an edge from 3 to 2, and that's why this is also a symmetric matrix. So if you see, if you take a transpose, it remains the same, right? So this is how you represent a matrix. So it has 4 vertices, so it's a 4 by 4 matrix, and you can verify that the other edges are encoded correctly. So how do you determine using a non-deterministic Turing machine if a given graph has a K-clique? So what we do is the following, right? We non-deterministically choose a subset. Okay, so how do we choose a subset? Let's say there are n vertices, right? N vertices, 1, 2, 3, 4, and so on. You decide non-deterministically to select one or not. Maybe 1 is selected, okay. Maybe 2 is not selected, so you don't select it. Maybe 3 is also not selected. Maybe then 4 is selected. Maybe then 5 is selected, and so on. You select some vertices, right? So 1, 4, 5, something. And then you check whether this set of vertices that you have selected, it's a subset of vertices, whether this forms a clique. This forms a K-clique, right? So first you non-deterministically select a subset of vertices, right? So you go 1, you include or exclude. 2, include or exclude. That's what I've written here. You non-deterministically select or omit a vertex I, and you write each of these vertices that are selected on the tape, right? So first you want a K-clique. If the number of selected vertices is not K, you can automatically reject, right? Because you are looking for exactly K vertices. If it is equal to K, meaning if you have non-deterministically chosen a set of size K, then for that chosen set, whether you check whether it is a clique, meaning if there are 3 vertices that are selected, let's say K is 3, you check whether all the possible pairs of vertices form there is an edge between them. So if there are 3 vertices, you want a triangle kind of thing, right? And that's it. So you non-deterministically select or omit each vertex. So again, for vertex 1 you are selecting or omitting. So selecting maybe omitting is 0, selecting is 1. Vertex 2, again you are doing this, right? 0, 1, and finally you get to 2 power n possibilities because there are 2 power n vertices, right? Out of which many will not be subsets of size K, because 2 power n means all possible subsets. But so then they will automatically be reject. And for the subsets of size K, you check whether it forms a K-clique or not. If it forms a K-clique, it will be accepted, right? So if it is a subset of size K, you check whether for all the pairs of vertices, if there is an edge, right? So Aij equal to 1 means edge, or rather Ij is an edge. If even one of the pairs I and J is not an edge, you reject. That's what I am saying here. If you don't reject, you accept, meaning if you accept if only 2 things are satisfied. First of all, if all the selected vertices, the number of selected vertices is K, and all the selected vertices, you take any pair of them, there is an edge between them, right? So you first have this 2 power n possibilities, and then you check whether for each of these possibilities whether it is a clique or not, a K clique or not. So some of them will be accept, some of them will be accept, some of them will be reject, right? If the graph has a k clique, then there will be at least one of these guesses, because we are trying, the guesses together span all the possibilities. At least one of them will correctly guess the k clique that is there. But if none of the subsets of size k form a clique, then all of them will be rejected. So either if they are not of size k, they will be immediately rejected. If they are of size k, they will be tested. But since none of the subsets of size k are going to be a clique, they will automatically be rejected. So if there is a subset of size k which is a clique, it will accept, which is what we want. If there is no such subset, they will be rejected. All paths will be rejected, right? So that's how we not deterministically test whether the given graph is a clique, right? Again, the number of here all the non-deterministic choices are made in parallel, right? Or parallel. It's not even parallel. In fact, non-determinism is kind of a abstract concept where if there is a path that leads to accept, you just are able to find it, right? So it's not like we are searching this path and then this path and then this path. It just automatically you just select the correct path if it is there. So the time taken is to make the choice and then verify it. So one point I want to quickly mention about the two non-deterministic non-deterministic choices or problems that we did. In the case of compositeness, we first non-deterministically chose x, then non-deterministically chose y, followed by a verification or a checking whether x multiplied by y is equal to the number, right? And if x and y are greater than 1. Even here, Clique also, it's something similar. We non-deterministically chose a subset, followed by a verification where we check whether the subset is indeed a k-sized subset, then checking whether it formed a clique, right? So in both the cases, we did some guessing, meaning non-deterministic choices, followed by checking whether these choices led to the desired answer. The point is that this is kind of a model where you guess something or non-deterministically choose something, then you verify, right? And the point is that any non-deterministic computer, non-deterministic Turing machine, we can do this. We can move all the non-deterministic choices right to the beginning. So there will be a beginning part where we make a bunch of non-deterministic choices, followed by a deterministic verification, right? So once I choose a subset in the Clique problem, once I choose a subset which is non-deterministically chosen, once that subset is there, then the rest of the verification is entirely deterministic. I need to check whether k vertices are selected, whether the number of selected vertices is equal to k, which is completely deterministic process. There is no choices or choosing happening. And once I am given a subset, I am just checking whether each pair of vertices form an edge between them. That's also a deterministic process. So in any non-deterministic Turing machine, we can reorganize the operation in such a way that all the non-determinism happens right at the beginning. Such a non-deterministic Turing machine is also sometimes called a guess and verify Turing machine, right? So this is something that I wanted to say. So guess and verify means all the guesses at the beginning followed by the verification. So again, guesses are another word for a non-deterministic choice. And I think that completes this lecture number 30, right? So we discussed non-deterministic Turing machines. We saw examples of compositeness and k-clique. We also explained what is the acceptance conditions. So you accept a string given as input if at least one of the many non-deterministic paths lead to acceptance, right? If there is at least one accepting computation path out of the many non-deterministic choices, you accept. If all the paths are rejecting, then you reject, right? So yeah, so this works for both k-clique and compositeness. And so one may wonder, because non-deterministic, we saw non-deterministic finite automata, which seemed to be more powerful because you could make multiple choices, multiple movements. But eventually it became equivalent in power to deterministic finite automata, right? Because both of them, the class of languages captured by both of them were the regular languages. Similarly, one can ask here, the set of, we saw deterministic Turing machine, and non-deterministic Turing machine is clearly at least as powerful, because we can do without making all these choices. We could always have exactly one choice. We can have for all the state and symbol pairs, we could just have one possible option, in which case it is same as deterministic Turing machine. So are non-deterministic Turing machines more powerful? Do they recognize some language that deterministic Turing machines do not recognize? Do they decide some language that deterministic Turing machines do not decide? So this is something that is a natural question at this point, and the answer is no. In fact, whatever can be decided or recognized by a non-deterministic Turing machine can also be decided or recognized by a deterministic Turing machine. So that particular thing we'll see in the next lecture. As far as lecture 30 is concerned, that's it, and so see you in the next lecture. Thanks.